Let's get started for the day. So let's just begin. Do a little business. So first of all, I hope you had a wonderful spring break. Hope you enjoyed it. Hope you got some good relaxing in, and that we'll be ready to go to sort of finish up our semester. Um, I'm still pretty injured, quite a bit better than I was on Tuesday. So you all will probably get a more cogent version of me than the people who met on Tuesday got. But I'm still reasonably injured, so we're probably going to try to go pretty fast today. Sitting at a computer is not working great still, so I'll try to sort of just talk our way through the problems as quickly as I can. I haven't been able really to do any grading for about a week now. Which means that I'm still quite a bit behind, unfortunately, on where I was hoping to be in terms of grading the last exam. I haven't even really started grading that last exam, which is not great. I think what I'm probably going to do is I'm probably going to make the subsequent exams a little bit shorter so that I can get caught up. So you'll have an exam that's due this weekend, and it's probably just going to be a bit shorter than it normally would be. The topics will be what we're going to talk about today, and then the material from the week before spring break in chapter 6. And hopefully, I am starting to get a little bit better. So I'm hoping this weekend I'll be able to grade that last exam, and then start getting everything caught up for the rest of the way. Let's see, any other business? Yeah, I think that's all I've got business wise. Do any of you have any questions for me about the remainder of the semester or anything within it? All right. Awesome. And like I said, let's just dive right into it. But my guess is we're going to go 40, 45 minutes, something like that today. And then hopefully by next week, I'll be more or less back to normal anyway. That's my hope. So I'm going to be relying a little bit more heavily than normal upon those pre-class videos to sort of introduce all the concepts. We're just going to dive pretty much straight into the problems. So let us begin with that. And remember, you have the ability to unmute yourself, so don't hesitate. Unmute yourself whenever you have any questions. You can also send things through the chat as well. Though those might take me a little bit longer to find, but I definitely will respond there too. So the host still be asking me questions and stuff. My deck's not that bad. It's just I don't want to sit for too long. So all right, let's get started with today's topic is statistical inductive arguments. So unlike improbative inductive arguments, these arguments work not by so much giving you good reasons to believe that a conclusion is true. They do that too to an extent, but they work by telling you exactly how likely it is, if it's a good argument, that the conclusion is going to be true. So they're still inductive in that the conclusion's not certain. We're not dealing with certain conclusions with either statistical syllogisms or inductive generalizations, but rather what we're given is, grounds to make a really well-educated guess, right? And guess the more likely outcome rather than the less likely outcome. That's sort of how the best way to sort of think about this. Again, just like the earlier inductive arguments we were talking about, you rely on both of these kinds of arguments all the time. These are not things that you don't do, things that you're unfamiliar with. You use statistical syllogisms all the time, and frequently in cases that are so obvious to you, you don't even think of them as arguments, right? But despite that, our goal is going to be, again, to sort of just get a little bit better at doing what it is you already do, to sort of understand these arguments, recognize them when you see them. And then with the second kind of argument we're going to talk about, inductive generalizations, the goal is going to be to sort of do a better job of almost recognizing them when you see them and read how they were sort of done. Statistical syllogisms we can do without an enormous amount of math, but inductive generalizations in particular would require an enormous amount of math to do well. You could have a statistics class that was really just dedicated to that kind of argument. And we're not going to do any of that. We're going to try to sort of skip the math. But at the very least, I want you to understand inductive generalizations when you see them, have some idea how they're working, and I want you to be able to recognize sort of obvious mistakes when you encounter them. So that's going to be our goal with these two different kinds of arguments that we'll talk about today. We're going to add two new fallacies to our fallacy list. We're going to add the fallacy of incomplete evidence. This fallacy only occurs and only takes place in the context of statistical syllogisms. So this is one place where I see students sort of sometimes make mistakes in exams. The fallacy of incomplete evidence, that's only a statistical syllogism fallacy. On the other hand, the fallacy of biased statistics, right? This only occurs in the context of inductive generalizations. So make sure you know how these two fallacies are different, that you keep them separate on the course of the exam. All right, so that was just a very brief little intro. Any questions, comments, thoughts, anything to start with? All right. Then if no one's got anything to start with, why don't we just start working our way through the questions? So the first group are statistical syllogisms. These problems, you have a lot less to write actually than you've been writing for the exam for the inductive argument so far. This will be pretty much like a sentence or two will be good enough. Not even really two would probably be too much most of the time. A good solid sentence is really all you will need to write for any of these problems. So what you're going to be asked to do and what you'll be asked to do in the exam will look exactly like this. You'll sort of be given four choices, right? You'll be given a statistical syllogism, and then you have to sort of evaluate it. Say either that you think based according to the argument that the conclusion is very likely to be true, right? And it won't always be a number, but let's say we mean something like by very likely, something like more than 75%, something like that. It should be pretty obvious on the exam and on these problems if we're talking about more or less than 75%. Second option, that the conclusion is somewhat likely to be true. Right? So that's sort of less than 75%, but greater than 50%. Third option, that the conclusion is unlikely to be true based on the argument. And so therefore, you're saying that that's one way of saying that you're looking at a bad statistical syllogism. And then the last option, the fourth one, that you're saying the argument commits the fallacy of incomplete evidence, which is to say that the argument does its math incorrectly, basically. And so that there's no useful statistical information contained within the argument, and so it can be rejected for that reason. So one of the things we're going to try to get clear about is how saying that a statistical syllogism is bad for number 3 is different from saying that a statistical syllogism is bad for number 4. That's one of the things we'll try to work with. But for now, let's start with something that's supposed to be pretty straightforward, not a trick question or anything. Why don't you look at number 1? Tell me how likely is the conclusion to be true based on the information you've got available to you. All right. So in this question, we're not, it's not a trick, not a trick question here. Right? How likely is the conclusion to be true? It's somewhat likely, right? We can indeed say exactly how likely. There's a 50.1% chance that the conclusion is true. Right? We've got the world's worst jail in the history of jails. At least I hope there's no worse jails than this, where almost half of the people within the jail are indeed not guilty of anything. Right? Slightly more than 50% are guilty by, one person, 50.1% chance. Right? We are told no other information about Joe other than that Joe is in the jail. Right? That's the only thing we know about Joe. We don't know anything else. And so therefore, based on the information we know, the information we have available to us, how likely is it that Joe is indeed guilty of a crime? 50.1% chance, right? That's how likely anyone would be, and we don't know anything about Joe to differentiate him from everyone else that's present within the jail. And so one way you could sort of characterize this or think about this, right? If you were forced to guess, you would guess that Joe was guilty. But you would really not be confident in that guess, right? I mean, it's barely better than 50-50. It would be rational to guess that he is guilty. I mean, it wouldn't make sense to guess that he's not. That's less likely. But nevertheless, you're not really confident in the result or confident in the conclusion, right? Because of how close it is to the 50-50 mark. All right, how are we doing with this question? So this one's pretty straightforward, pretty easy. There's no trick here. Any questions on number 1? All right, do the same thing with number 2. All right, again, this one, no trick here. This is, again, pretty straightforward. Same exact setup, right? We don't know anything else about Joe other than the fact that Joe is in the jail, right? That's all we know. The only thing that's changed is that now this is a much better jail, right? There's a much higher percentage of people in jail who are indeed guilty of a crime, right? And so we can say then that this conclusion is now very likely to be true, right? And again, we can say indeed exactly how likely is it? 97.5% chance. And again, this doesn't have to be a specific number. Sometimes you might see, like, maybe this would be written, the overwhelming majority of people in this jail are guilty of the crime. Same thing, while that's not a specific number, it's sort of a standing in for a percentage, right? The overwhelming majority, that's a really high number, right? That's a really high percentage, right? And so since we, again, don't know anything else about Joe, other than the fact that Joe is present within the jail, the only logical guess would be that Joe is indeed guilty, and you'd be quite a bit more confident at this time, right? There's a much better chance that Joe is indeed guilty of a crime because this is our better Joe. Note, though, that this is dependent upon not knowing anything else about Joe, right? If we change the scenario slightly, if I was to say Joe is a guard within this jail, all of a sudden, some things have changed dramatically. Right now, we know something different about Joe merely than the fact that he's in jail, and you suspect that the percentage of guards in the jail that are guilty of a crime are very different than the percentage of people in general in the jail who have committed a crime. But based on the information we had originally, right, the only sensible guess would be indeed that Joe is guilty of a crime, and you'd be very confident in the result. All right, how we doing so far with these first two? Questions, thoughts, comments? See here. All right, let's go on to number 3. All right, my hope is that when you sort of read this argument, your initial reaction is that something seems to be wrong, right? And indeed, something does indeed seem to be wrong. What is it? How can we sort of characterize the mistake? This is an example of the fallacy of incomplete evidence. So here we have our first sort of instance of a bad statistical syllogism. We know things about the appointed ambassador from China to the United States, other than the fact that this ambassador is someone from China. Again, note here, we don't have a specific percentage, but that doesn't matter, right? Most people, right? What does that mean? It means more than 50% at least, we could say, right? And so if all we knew about this person was the fact that they were someone living in China, it would indeed be entirely reasonable to assume that they did not speak English. But we know something else about the individual. We know they're the appointed ambassador from one country to another. And almost always, I imagine, it's probably the case that ambassadors speak the language of the country that they're going to. It's sort of like a prerequisite or a condition for being an ambassador is that you speak the language. Every country the US sends ambassadors to, they always send someone who speaks that language. Okay? And so we suspect that something's gone wrong, if you want to put it this way, with how the math was done in formulating this most people, right? How the statistic was generated. It wasn't looking at the right group, at the relevant group to tell us how likely the ambassador is to speak English or not to speak English. That's what we mean by the fallacy of incomplete evidence. The math is sort of done wrong. You're not looking at the right group. Right? Ambassadors are far more likely to speak language than the average person within a country are. Right? And so since that's not being taken into account in how the most people, quote unquote, was getting calculated, the argument just gives us no useful information. And that's what we mean when we say it commits the fallacy. Right? It tells us nothing of statistical value in determining how likely the ambassador is or is not to speak English. All right, how are we doing with 3? So we have our first example of a bad statistical syllogism, and it's our first example of the fallacy of incomplete evidence. All right, then let's move on to number 4. All right. Here, we again have a bad statistical syllogism. Again, my guess is if you just sort of heard this one randomly, something would seem wrong to you. Something would seem off. But this argument fails in a slightly different way than number 3 does, and that's why I wanted to sort of juxtapose them with one another. Right? In this case, the conclusion is just really unlikely to be true. It's making the wrong guess based on the statistical evidence available to us. But the 10% number actually is probably quite useful in figuring out how likely it is or is not that the individual is going to be able to get into Harvard Law School. Right? We don't know anything about this U, right? We don't really know anything about them, right? Maybe they're a qualified applicant. Maybe that's it, though. We don't know anything about them that would make them exceptions to this rule. Right? And so as a result, what would the rational guess be? It would be that they're not going to get in, not that they are going to get in, right? But the difference is that whether or not this 10% number is actually useful. We can use this 10% number in this case to guess how likely this individual is to get in. Whereas in the case of number 3, where the fallacy was committed, the fact that most people in China don't speak English is irrelevant, or not, maybe not completely irrelevant, but it's not useful statistical information for us trying to figure out how likely the ambassador is to get in. Here, this 10% number is useful for figuring out how likely it is that the individual is going to get in, but it just is not being used correctly. It's sort of being applied in an incorrect way. And we can see this a little bit looking at 5. So we just go real fast at this one. The same basic argument, just with a slightly different conclusion. Right? We change the conclusion to you probably should not plan to get in. All of a sudden, then this has become a very good argument. Right? The conclusion is very likely to be true, right? Because it's sort of just reaching sort of the inverse conclusion. Whereas this most people thing is just useless here. It doesn't give us any useful information about how likely the ambassador is or is not to speak the language. So that's really the key thing to sort of distinguish when you're working on these problems, both for your own sake and on the exam, is really keep telling these 2 different ways of the arguments failing apart. Right? So how are people feeling with the difference between 3 and 4? Does anyone have any questions about how those 2 are different? Why one is committing the fallacy and the other is not? All right. And note, if we knew something else about you, right, you, quote unquote, in this problem, right, things might well change. If you, a high school debate champion, probably should not plan to get in, all of a sudden the argument would commit the fallacy. Right? We would know something about you other than that you are a qualified applicant. Right? And one would easily imagine that a high school debate champion is more likely than the average person to get into Harvard. Right? How much more likely, we don't know. Right? But the 10% is just no longer a particularly useful number. We can't formulate any good guesses based on that 10% because of the additional information that we have available to us. All right, let's do one last example for statistical syllogisms. Look at number 6. Again, my guess is you read 6 and you probably were like, yeah, something's wrong here. Something's not right. And this is a super strange argument, actually. It's a very odd one to even consider, right? The logic of it is, though, entirely analogous to previous problems we've looked at, right? Is it true that the overwhelming majority of people present in a courtroom are not guilty of murdering the victim? Yeah, right. Who's in the courtroom? We've got people like the jury. We've got maybe people in the audience. Maybe we've got the news media, the judge, the prosecutor, the defense attorney. And yeah, most of those people are not indeed guilty of killing the victim, right? But we know something about the defendant that differentiates them from the other people present in the courtroom, and that's that they are indeed the defendant within a court trial. Right? Again, if you want to put it this way, that it's just probably way more likely that the defendant in a trial is guilty of a crime than the other people present in the courtroom. Right? And so that for that reason, the argument is again committing the fallacy of incomplete evidence. Now, note that doesn't mean that the defendant is actually guilty, right? That's what it means when we say that if someone completes the fallacy of incomplete evidence. You can't just reach the opposite conclusion. Right? What we're saying when we say that the argument commits the fallacy of incomplete evidence is that the argument just isn't telling us anything useful. It's not giving us useful statistical information because, again, it did the math wrong. It didn't calculate the relevant percentage. If this had been how likely is it that the defendant in a murder trial is guilty of a crime, then maybe it would be useful evidence. Right? But that's not what it is. And so there is no useful evidence whatsoever here to tell us whether or not the defendant is or is not guilty. All right. So those are the only examples I was planning on us going through for these statistical syllogisms. Again, does anyone have any questions about anything with any of the statistical syllogisms we talked about so far? Any of the just broader concepts involved in the statistical syllogisms? All right, then let's turn to inductive generalizations. So inductive generalizations are a scenario where you're going to need to write a lot more. So a statistical syllogism is like a quick sentence is enough. If it commits the fallacy of incomplete evidence, basically just briefly tell me what the incomplete evidence was, what's being left out of the statistics, basically. If it's not that, you can probably, if you just say the conclusion say is very likely to be true, you could just say that, right? Maybe just give me the percentage or something. Right? For inductive generalizations, you're going to have a lot more to write. This will look more like the previous inductive arguments that we've been talking about. And there'll be a couple different steps that I want you to sort of follow in the course of addressing the question. So your overall goal is going to be just to evaluate the inductive generalization. But along the way, there's sort of intermediate things that will help you do that. So for all of these problems, and again, on the exam, it'll look exactly like this. I'm going to want you to first identify the sample group and the overall population. I think that really is valuable to do. It might seem unnecessary or it might seem obvious, but the only question that matters in the course of evaluating these problems is how good of a job does the sample group do of representing the overall population? That's it. That's the only question you should ask yourself. And so really clearly and explicitly identifying the sample group and really clearly and explicitly identifying the overall population is super valuable to that task. Second thing you got to do, you got to describe the sampling method that was used. Basically, how was the sample group formed? What technique was used to formulate the sample group? And again, you don't need to be exhaustive with it, but a sentence, maybe a sentence or two, just telling me the method that was used. Right. Third, you should identify any margin of error that's present within the conclusion. We'll talk about margin of errors a little bit in a minute or two. And then lastly, sort of the big thing, right? You have to evaluate the arguments and identify any fallacies that are present within it. There are two big picture fallacies that are relevant for inductive generalizations. So the first is a fallacy we've already talked about, the hasty generalization fallacy, right? Only now we can sort of rethink that fallacy in statistical terms. The hasty generalization fallacy is where the sample group is so small that it could not possibly represent the overall population. It's just too small for whatever sampling methods you use. It's just too small to possibly, right, represent. That's something you can actually calculate mathematically. It is possible to mathematically calculate exactly how large a sample needs to be for it to possibly be representative. We're not doing math. As a result, you should not super worry about the hasty generalization fallacy for these problems. You don't have enough knowledge and statistics basically to calculate how large a sample can be. Frequently, samples can be dramatically smaller than you would guess and still give useful results if they're done properly. And again, that's just outside the scope of what we can talk about in the class. The fallacy that is relevant, the new one we're going to add, is the fallacy of bias statistics. This is the main thing I want you to be checking for. The fallacy of bias statistics is where there is some problem with how the sample group is formed. So there's a problem with the sampling method, such that there is a systematic bias and such that people are in the overall population are being systematically excluded from the sample group. So we'll talk about that more. We'll do some examples of that as we sort of go. But for this last step, that's the main thing you should be looking at. Is the fallacy of bias statistics being committed? Yes or no? That's the main thing. The question of whether or not hasty generalization is taking place is just a little bit outside of our scope to do too much with. All right. So that was my introduction. Any just questions about that quick introduction? All right, then why don't you start working at number 7? I'm going to give you actually a couple minutes for this because it's a little bit longer. So try to work your way through all 4 of those questions on number 7. All right, let's start working our way through these 4 questions with this first argument. So first question, what is our sample group? What's our population? Right, the sample group is the responders. So not all 3,000 actually, because all 3,000 of them didn't necessarily respond. But the responders from the 3,000 adults who are randomly emailed their cult from across all 50 states, yada, yada, yada. Right? So that's our sample group. That is the group that is sort of being used to try to figure out what's true about all adult Americans. And so we're not just talking about, say, Americans who vote or whatever, right? We're talking about all adult Americans. Okay? The only relevant question then, if this is our sample group and our population, is how good of a job does this sample group do of standing in for all adult Americans? If it does a good job, right, it's a good inductive argument and it can help us make useful predictions about what will be true of the overall population. If it doesn't, right, then it's a bad inductive argument and it does not help us make useful predictions or accurate predictions. All right. So what sampling method was used? How are these people within our sample group selected? Right. What was used is a technique called stratified random sampling. And this is the sort of best methods, best practices for use if you are going to do this kind of opinion poll or this kind of survey. All right, so let's go through the 2 parts of it, the randomness and the stratified part. So do randomness first. The people involved were selected at random, right? We're told that they should just randomly email people. You imagine maybe it was a random number generator or something was used to do this, to generate this. Why is that good? That's good because if I individually tried to select these 3,000 adults, there's a chance that some idiosyncratic bias of mine is going to negatively impact who gets selected and who doesn't. Right? But the sense is of randomness is kind of fair. There's no sort of biases built into randomness. It's just picking numbers out of a hat or picking names out of a hat. And so we don't need to worry about the random number generator itself possessing any biases. Then let's go to the stratified part. The stratification part is that where randomness can go wrong potentially is if we just get unlucky in the names we pulled out of our hat. Right? Let's use some examples of this. We're talking in this case about Medicare. Right? And I think we would imagine that different kinds of people are probably likely to feel differently about Medicare. So I'll just do some examples. My guess is older people probably would feel differently about Medicare than younger people. My guess is that richer Americans, Americans with more money, probably feel differently about Medicare than poorer Americans, Americans with less money. Not, again, not always, but just statistically, right? There's probably like variation on the basis of those factors. And again, maybe Democrats feel differently about it than Republicans, or maybe people from some states feel differently than from other states, or yada yada yada. Keep on going down the list, men, women, but whatever. Keep on going through it, right? We would suspect that these various kinds of, you think about it as demographic data, that it might well influence how people feel or don't feel about Medicare. All right. It's possible we could just get really unlucky, though, with selecting names out of the hat with regard to representing all Americans. So let's just use this as an example. I think it's something like 35% of adult Americans are registered Republicans. It's something like that. Let's say we got really unlucky when we were pulling names out of a hat, right? We were using our randomness, and instead of getting 35% of the people we picked out of the hat being Republicans, instead it was only 10%, right? We just got really unlucky, or maybe we got really unlucky with the people who chose to respond to us, right? Maybe just less Republicans responded than other groups or whatever, right? So we would want sort of 35% of the people we polled to be Republicans, but we only got 10% as Republicans. Again, switch it with Democrats, same issue, right? How can we fix this? We can fix this using what's called stratification, right? Where we can basically weigh that 10% of people as if they were 35% of all responses. Right? So we know 35% has some demographic information. We can weigh the responses we got to match that 35%. Similarly, with people representing states, similarly representing any other demographic group you want, with the old, young, rich, poor, again, yada, yada, yada. Right? We can weigh these various demographics so that they match what's true of the overall population. And using stratified random sampling, it's possible to get by with surprisingly, almost shockingly small sample groups and still get useful results. You can actually get, if you do it well enough, useful statistical information for all 300 million Americans out of maybe as few as 500 people, if those 500 people are selected well enough. So stratified randomness, that's our sort of best method. So probably we're looking at a good argument here. We'll talk about that a little bit more as we go, but that's probably what we're looking at. So just pause here for a second. Any questions about any of these first two steps of answering the problem? Or any questions about what I meant by stratification or randomness, or why it's good, why it's valuable to method? All right, let's move on to our third question then. Let's move on talking about the margin of error. So in this case, the margin of error is plus or minus 3%. Right? So we're told that within the sample group, it was sort of exactly 53% of people, but the conclusion is 50 to 56%. So it's not exactly 56. We said the way that usually gets characterized is plus or minus 3%, right? So from the 53% that was true within the sample group. Let's pause for a second though, because margin of errors people frequently find a little bit counterintuitive. And I actually try to answer this question. Do it in the chat. Unmute yourself. Right. Say on the exam I asked you, hint, hint, I'm going to ask you this. So let's say on the exam I asked you, if an argument contains a larger margin of error, does that make the argument stronger or weaker? Which answer would you give? Go ahead. We got a brave person in the chat. Let me pull the chat open because I want Zoom to show me the chat. All right, let me just close out of this for a second. So someone's saying it makes the argument stronger. Does everyone agree that it makes the argument stronger? Anyone want to make a claim for weaker? Good, you're right. And that should be super counterintuitive. You are correct. Larger margin of error makes the argument stronger. But you might say, wait a second, I'm confused. How does a larger error make a better argument? That seems off. It seems weird. It seems counterintuitive. And in most classes, at least, maybe many of you are just being quiet, but most of the time when I've asked this question, most people, their gut reaction has been a larger margin of error makes an argument weaker. So let's try to make it really clear why you're right, in effect, that the larger margin of error makes a stronger argument. So let's think about it like here. So we have 9 people in the room right now. All right. So let's say I was to make the prediction exactly one of us in this room, exactly one of the 9 of us, have a January birthday. And I do, so I'm a January birthday. So I'm that one. Right. So what does that mean? How likely is it that my prediction is going to be right? Well, it would be really easy to disprove me. Like, I mean, really easy to make disprove my prediction. A single one of you having a January birthday would be enough to make my prediction wrong. That would be enough to falsify it. But let's say instead I made a weaker prediction. Right? I gave myself a little bit more wiggle room. Let's say I said 1 or 2 of us in this room have a January birthday. Is it more or less likely that my prediction is going to be right? Well, now it's more likely, right? One of you could still have a January birthday without making me wrong. That's how to think of these margin of errors. Margin of errors are giving yourself, or the person doing the argument, making the argument, is giving themselves a wiggle room to be like a little bit off, but still have their prediction be accurate. So in this case, let's jump back here. So in this case, if the margin of error is plus or minus 3%, right? I'm not saying, or the person making the argument isn't saying that exactly 53% of adults believe this, but something around 53% of adults believe this. We say that inductive arguments are stronger, the more likely the conclusion is to be true. It is more likely that the right answer is somewhere within 50 to 56% than it is that the right answer is exactly 53%. And so the larger the margin of error, the stronger the argument becomes. What's the downside then? Why not just make the margin of error huge? It's also true that the larger the margin of error, the sort of less useful the prediction is, right? There's 9 of us. If I said 1 to 9 of us have a January birthday, all of a sudden I've made no useful prediction at all, right? Similarly, if we said, 40 to 60% of all adult Americans would be opposed to making any radical changes to Medicare, again, the prediction is useless now, right? It's either a pretty large majority would be opposed to it, or a pretty large majority would be in favor of it. And that information doesn't tell us anything. Or the example I used in the video, right? If we're trying to predict who is going to win a presidential election, and I said, 43% of people to 63% of people are going to vote for Hillary Clinton, I can't make a good prediction on the basis of that information. So 1, larger margin of error makes the argument stronger, but 2, larger margin of error makes the argument less useful. So pollsters will always try to balance those things. And usually the margin of error is plus or minus 2 to 3%. That's usually about the range where people aim for. This still does indeed tell us something useful. Right? If we made it too much larger, it's probably going to start getting quite a bit less useful. All right. So any questions with how margin of errors work? All right. Then let's go to our final question. Let's evaluate the argument. Right? And in this case, I think we're looking at overall a reasonably strong argument here. There's good, and so the way to say that, you should always basically say a sentence like this. Why is it a strong argument? It's a strong argument because there's good reason to believe that the sample group will be representative of the overall population because of the sampling method. That's really the only concern you should have here. We don't know exactly how many adults responded. We were told 3,000 were sent the question. We don't know exactly how many responded. If it was only 2, that's not going to be enough. That 2 people can't possibly represent all Americans. But if we, it's our percentage is 53%, so it's got to be at least 100, and it's probably more than that. So, we have good reason to think that it's probably a large enough percentage of people responded that we can get useful information from our sample group. It's large enough that in principle it could represent the overall population. So we can say that the argument avoids the hasty generalization fallacy. More importantly, where you should focus your answer on, the only bias this sampling method introduces is that, and let's stop for a second. What do I mean by bias? I mean by bias the only people who are being systematically excluded from our sample group. Who are they? The only people getting systematically excluded are people who chose not to respond. People who choose not to respond to the survey will not be included within the group, even though they might have been included within the initial randomly selected 3,000 people. Right? They're not going to be represented within our sample group because our sample group is only made up of people who responded. Right? Now, this is not a negligible concern necessarily. There's actually a lot of concern. The last couple political campaign elections that took place, the polling wasn't wildly off. It wasn't as off as a lot of the media was making it sound like it was, but it was off a little bit for both of them, though not super for the last one. But the 2016 election was off. Was noticeably off. There's one reason why people are trying to figure out what was the mistake, what was wrong with the sampling method, is that it increasingly might be the case that smaller and smaller numbers of people actually are responding to surveys. So let's do a quick opinion poll for the 9 of us in this room. Would any of you respond to a random phone call from a number you did not know and pick up your phone at all, let alone sit through a survey? None of you? So you got chat, and if the chat will ever come up. God, I don't want the chat come up. Yeah, but I'm getting a bunch of no's. I can add myself to the list as a no. Yeah, I too don't do that. I can't recall the last time I answered a phone call from someone and I didn't know who was calling me already. Right. So far, at least, no one has said yes. None of the classes that I've taught so far this year, not a single student has said that they would answer the phone under such circumstances. Similarly, if you got a email asking you to fill out a survey, how likely are you to fill that out? Again, probably not super likely. You got shit to do, right? I mean, you probably more open the email at least, or more likely to open the email. But again, probably most of you wouldn't respond. Last year, I believe I had a 5% response rate from my course evaluations. I'd like a better this year. I really do like those course evaluations. I take them seriously. But yeah, the evidence just is that increasingly small percentages of people are actually willing to respond to these surveys. What would make that a problem? Well, what would make that a problem is that the people who responded were, statistically speaking, weird. Right? I don't mean weird like in a bad way, just like weird statistically. If there's something statistically different about people who are likely to respond to these surveys than people who aren't, that would indeed be introducing a kind of systematic bias into the affairs, right? If, say, some people have theorized, I don't think there's great evidence for this, but as some people have theorized, if conservatives are less likely to respond to these things than liberals, you might have a liberal bias in the poll, not because anyone deliberately did it, right, but just because conservatives aren't going to respond. So liberals will be sort of overrepresented. I don't actually, people have hypothesized this, but my understanding is that there's actually not really good evidence that that's the case. And actually, it's weirder than that. The people who respond versus not respond, it's not exactly liberal conservative. It's just a little bit stranger than that. The difference between the two. But regardless, that bias is indeed introduced by our sampling method. Right. On the other hand, there's kind of nothing we can do about that. There's no way to avoid it, sort of like holding people at gunpoint and making them answer surveys or whatever. And that's not really an option, right? There's kind of no way to avoid this sort of like violent force or compulsion, which is not a good idea either, right? And so this might be an unavoidable concern. There's no good way to correct it. All other bias is eliminated as a result of our stratified random methodology, right? No other bias is present. And so overall, we do seem to be avoiding the fallacy of bias statistics, and we seem to have a reasonably strong argument here. It would be entirely reasonable to guess that something between 50 to 56% of Americans hold this belief. All right. How are we doing with this problem? Any questions? All right, then let's go on to our last one for the day, number 8. Try to answer all 4 questions for number 8. All right, let's start talking our way through this last problem. So what is our sample group? Our sample group is the 96 actor or athlete owned restaurants. Right? These are the restaurants that are being looked at to determine how likely it is that a restaurant closes within the first 3 years. What's our overall population? Our overall population is something like all restaurants. It's important. It's not all businesses, right? This 33% of all new businesses statistic, we're not told where that came from. It's not coming from the argument itself. The argument is not deriving that percentage, right? The argument is sort of talking about how likely is it that restaurants are going to close. You could also have said here newly opened restaurants. That would be fine too. Those are functionally identical because all restaurants were newly opened restaurants at some point. So they sort of like come to the same thing. They sort of would come to the same end. So I would have accepted either answer as either all restaurants or all newly opened restaurants on the exam. All right. Any questions there with just what the sample group and population are? People good there? All right. Let's talk about the sampling method then that's been employed. How these 96 restaurants were selected, right? And they were selected in effect by the magazine choosing specific restaurants to study. Now, this is obviously not best practices, right? It's not the best technique, not the ideal technique to use. No randomness is being employed at all, and there's no stratification being employed at all either, right? So that's a danger, right? That's not the best thing. But that in and of itself isn't enough for us to say that we should reject the arguments, right? I mean, doing the kind of sort of stratified random sampling study that was done in the problem number 7, that just takes a lot of resources. You need a lot of money, you need a lot of time, you need a lot of personnel, right? You need resources, you need reach, you need a bunch of stuff that people don't always have, right? And so sometimes you do have, you will in the course of doing this kind of inductive generalization, you'll have to rely upon subpar methods. What matters is what danger do those subpar methods introduce? And in this case, the danger that's introduced by this sort of subpar method is that there'll be some bias in how the magazine in this case selected these specific restaurants. That for whatever reason, either intentionally or unintentionally, they're going to select restaurants that are not representative of all restaurants. There'll be something different about the restaurants that are selected that make them a poor stand-in for what's true for all the restaurants. And so what you'll need to figure out is, has that danger been successfully avoided or avoided as best as possible? Or is it taking place and is the argument committing the fallacy? Before we answer that question directly, let's talk about the margin of error question. So in this particular case, the argument doesn't really have any explicit margin of error. And so you could just say that there's no margin of error, no mathematical margin of error. I guess you could technically sort of find one. So what is the exact prediction that should be? The exact prediction should be opening a new restaurant that's 20% versus 33%. Should we say that it's exactly 13% safer to open a restaurant than some other kind of business versus the sort of quite a bit safer that we actually see in the conclusion? You could sort of say that's kind of like a margin of error, or margin of error of a sort, but it's not really like a numerical statement. It's sort of a qualitative kind of wiggle room rather than a numerical one. So it would be fine if you saw a problem like this in the exam to just say that there's no explicit margin of error given at all. Any questions with this one? All right, then let's get to our overall conclusion then. Is this a good or bad argument? And I think we would want to say this is indeed a weak inductive argument. And why? Because it commits the fallacy of bias statistics. So here we have an example of the fallacy of bias statistics. There is a systematic error introduced by the particular sampling method that was used in this case, right? Namely, actor and athlete-owned restaurants probably are not representative of all restaurants. Right? And why not? Right? Well, if you're an actor or an athlete, you have certain kind of advantages that are going to be conducive to your restaurant staying open longer than restaurants that don't have those advantages, right? So maybe, if you're famous and wealthy, right? So maybe you can sort of afford to run at a loss for a while. Maybe if you're, an athlete or an actor or something, you have a large social media presence, so it'll be easier for you to advertise your restaurant, and so on, right? There'll be various kinds of advantages that you might possess if you're an actor or an athlete that will make your restaurant stay open longer, right? And so therefore, those restaurants do not represent all restaurants well. there is a systematic class of restaurants that don't have these advantages that are excluded from a sample group. And so again, as a result, the math is just done poorly. The math is not done well. There's no useful information we can get from this 20% number. It's just not actually representative of all of the restaurants that we're supposedly talking about. All right. How are we doing here? Everyone see how this fallacy is working, what I mean by this fallacy? Any questions about either of these inductive generalizations or anything else? All right, we can start winding down a little bit. I'm going to give you one more example of the fallacy of bias statistics, just because it's really funny, and I think it's sort of helpful or illustrative. So there was a study done, I believe, in the 90s, late 90s, or maybe it was early 90s, whatever, where they were trying to, a group was trying to figure out how dangerous car crashes were. And what they did was they sort of just like polled people who had been in car crashes. And they reached the conclusion that car crashes weren't really that dangerous at all, because everyone they talked to, none of them had died. And what's the obvious problem? Well, the dead ones aren't going to get back to you. The dead ones were not going to respond, right? The method they employed systematically excluded all of the people who had died in car crashes, or indeed maybe even ones who had sort of systematically suffered some kind of severe injury even within the car crash, right? Those people were systematically excluded, and so their data was literally meaningless. It gave us no useful information whatsoever. Okay? And rather than saying that with a bunch of math, we're saying that with this fallacy, right? So my hope is that you'll be able now, when you sort of see these studies, see these surveys, you'll understand a little bit how they're being done, why they work when they work, and what the pitfalls are. You can sort of recognize egregious mistakes, perhaps like that one. All right. So any last comments or questions for me today? All right. Then let's call it here. So just a reminder, we'll have the exam covering chapter 6 and this material over the weekend. It's going to be quite a bit shorter than the previous exams, I think, probably like 20, something right around 20 points. So what it currently says in Canvas isn't accurate because I haven't written it yet, but it'll be a little bit shorter than some of the past ones. Remember, it's for the statistical syllogisms, you can get it by with just a quick sentence. For the inductive generalizations, we're looking at a good paragraph or so of answer that needs to be done. Yeah, and then hopefully I'll probably try to hold office hours like normal on Friday. I think I should be feeling good enough to do that. Hopefully by next week I'll be fully back to normal, so we can hold a little bit more back to normal classes. I won't have to feel quite so rushed to get through everything. Yeah, hope you're all doing well. We're getting near the end. We're going to start winding down with things a little bit as we sort of move through after we get done with this exam. Yeah, so I will see you all next week. I hope you're doing well. And yeah, talk to you later.
Thank you.
Absolutely. Have a good one.
Thank you.